the video. Okay, Andrés, hello.
Yeah, hello.
Hi.
I guess I lost my internet connection for a second.
Okay.
Hopefully it will work now.
Okay. Yeah, you are sharing. Yeah, perfectly.
Yeah, perfect.
Fine. Thank you. Yeah.
Yeah, thank you. So yeah, I'm going to present my work, which has been done with Rodrigo Moreno from the Universidad Nacional de Colombia, and it's titled "Using Evolution to Design Modular Robots: An Empirical Approach to Select Module Designs." And the issue that we are trying to solve, or like to address in our paper, is it happens when you have like systems made of modules. It could be like in modular building, or we're using construction in concrete panels, or when you are just playing with your kid using Lego parts. I guess you are building systems that are made of these building blocks. And then you want to optimize these building blocks to generate better structures, or good structures. But the analysis of these building parts cannot be done, or is very difficult to perform in isolation without building a complete system. And this is also the case of, it happens the same on modular robots. The modular robots are autonomous units, robotic autonomous units, which comprise one or more actuators, a couple of sensors, computational capabilities. So the autonomous devices are able to decide and like the actions to perform based on its own information, sensory information, and also from messages from other models, because they can also communicate with other models. And important, they also have these attaching points between them. You can just have different connectors, and then you can attach these modules together to make a bigger robot, because usually one module alone cannot do much. Basically, most of them cannot even move. They can just move its own actuator, but they cannot locomote on a terrain. So in order to make robots which are they are able to work in an environment, you need to attach these modules between them, and then make like a configuration of modules. And for example, we have several examples, and they have been developed a lot in the robotics community, a lot of different systems. So you can see here, like at the left, you have the Ethmor modules, which are like kind of a sphere, and each of them has 4 connections, attaching points. And then you can make, like, for example, a snake module here, or you can just make also other kind of devices. You can have like the small system, or you can have like the M-tram system, and well, all of them are made of blocks. And we can also see my previous work. I guess this is like an heterogeneous modular set. So in this case, we have 4 different kind of actuators, and we can combine them to perform different tasks. For example, this manipulator here is performed or is built with a telescopic prismatic module, a hinge module, and a rotational module. And this is fully functional, I guess. Once we build it, attaching these modules together, we can just make like a functional manipulator, which is able to perform or move some nuts from one place to another, for example. Or if we just take a couple of hinge modules, we can just make a snake morphology. So in this case, it's able to move forward or backwards depending on the controller parameters. But the important point is that we are using these modules as building blocks to increase, to develop robots quite fast. The problem is that in robotics, these modular robots are usually designed by an engineer. An engineer designs, okay, the morphology of this module, maybe having 1 actuator, 2 actuators, different sensors, etc. And once these modules are designed, they should build a bunch of them, and then you put them in a bucket. And then when you have like a task to perform, another engineer selects the best morphology for that task at that environment. And then finally, the last step is to program this morphology or this configuration of robots of models in order to perform the task. Of course, in the evolutionary community, I guess we have tried to address the last 2 points. So we have we usually evolve the morphology or the configuration of models of the robot and the controller to perform a task. So these 2 points have been addressed, and this is like an example of one of our previous work, where we basically just have like a bunch of like a task, which is like locomoting a flat terrain, and we evolve the morphology and the controller, as you can see on the top picture, and then we can take the best individual and just build it quite fast in the real world, because this is made of models and it's just attaching some models and set some parameters of the controller. But the question that still remains is, okay, how can we just design the models to maximize the performance of the assembled robots? And this is like the question that we are going to try to address or shed a bit of light today. So basically, we are taking this platform, which is called Emerge. It means like easy modular robot, modular embodied robot generator. And is this simple model that you can see here? It's just one actuator, one motor, which is able to rotate along this black axis. And we have like magnetic connectors, one on this face and 3 others here, 3 female faces. So we can just attach very quickly these models between them to develop the robot. And also another interesting property of this model is that it's easy to build. So you can just take a couple of off-the-shelf parts and 3D printer parts, and then you can just build it very easily, because that's another issue in modular robots, is that it takes usually a lot of time to develop and build the models. So basically you only end up with a couple of models, so you cannot have a lot of them. And this model is open source. You can just visit this link, and you can just download the parts and all the things to build them. And then we are also using ad hoc evolutionary algorithm, which is called Ethmor, Evolutionary Designer of Heterogeneous Modular Robots, which is based on a direct encoding, where we have like a 3 representation of the morphology, where each node represents a model, and each model has its control parameters, and also like the arrows, like the connections between the nodes, represent like where it's going to be connected, the child node into the root node, like the face where it's going to be connected, and also like the orientation about how it's going to be connected. And then this algorithm makes a population of random controllers and morphologies, and goes through a series of phases. Where like first we have like a growing phase where we attach models in different random positions. Then morphological adaptation phase, where we just change some of the connections of the robot, trying to just adapt to the new model that we have added before. Then a control adaptation phase, where we just change some of the control parameters in order to just adapt to the new morphology. And then we just test, okay, are we just doing something which is nice or like improves the fitness or not? And we just have like this pruning phase, where we just remove all the models that do not contribute to the fitness. And finally, we have a replacement phase, where we just remove the worst individuals and replace them, half of them with random individuals to increase the variation of the population, and the other half with variations of the best individuals, where we just apply a symmetry mutation, because we have seen that symmetry usually improves the fitness of these robots. And in this paper, we are just trying to determine what kind of features it could be better for like designing these models. So we have tried different variations of models. We have the Emerge model, which is a rotational model, and it's active. It has one actuator, and we have tried to see, okay, if we extend the length between these phases of the motor, I guess it's going to be better. Are we going to get better results or worse results? And also we have also tried different kind of base models, like we use a base to start to assemble the whole robot. It's a completely passive unit without no actuators, and but we have like, it has different kind of sizes and also different kind of number of connection points. And then you can see here some of the results when we evolve the morphology and the controller for the task. More specifically, we have tried like this extension in length. We have tried different lengths, like the original design that we have designed a few years ago. And then we have tried 1.25 times its original size or length, and then up to 2, 4, and 8 times the original size of the module. And important, I guess, you can see here that I guess it's the same motor, so I guess the torque for all the models it's the same, but the weight increases with the length because we need to add more material for the structure. So I guess the weight of the model increases with the size of the actuator. And then for the cuboid base, I guess again it's bigger in size and then increases also in weight, but also we have, like in the cuboid, we have 5 attaching points, like at the top and 4 at the side. And for the flat base, we have like 16 different connection points, 4 connection points at each of the corners. And then the fitness is very simple. We just want to move as far as possible on a flat terrain. The only trick that we are doing is we just don't start to count the fitness as soon as the simulation starts, because usually the robots are they only have one module in contact with the ground, and then the robot usually falls. So to remove that transitory movement, I guess we just start the simulation at 2.5 seconds later. But the distance is basically the distance between the starting point and the final point. So some results you can see here. These are like different evolutions where we have like up to 25,000 evaluations for each evolution, and we have performed 20 independent runs for each of the experiments, and we can see like a clear trend. I guess we can see that in both using like the cuboid base and for the flat base, the results are very similar. We just get much lower fitness when using the long actuators, 8 times the original size of the actuators, a bit less fitness when we get like, a bit more fitness than the 8 when we get like the 4 times the length, and it's more or less very similar, like when there's almost no difference when using like 1 time the original length or 2 times the original length. So we can see that better in a box plot where we just compare like the best individual fitness at the end, and we can see here how the fitness decreases more or less linearly with the length above 2 times the original length of the models. And also we have performed an experiment where, as we are able to perform like evolution of heterogeneous modular sets, we can just try to perform an evolution where we just have all the different lengths available for the models for the robot, and the algorithm can just choose what's the best length for each module. So this is like here, the 1 to 8. We are allowed to the evolution to use any of the models, and in this case, the fitness is comparable to the best fitness, which is quite nice to see. But there's another thing that we have also analyzed is like the number of modules, of the best fitness of the best robots. And as you can see, when you have like models with 1 or 2 original lengths, or like I guess we get like much more modules than when we are using like longer models, like 4 times the original length or 8 times the original length. There's a drastic decrease in the number of modules for each robot, and this decrease of number of modules also can be seen when using these heterogeneous modular sets, like using modules of different lengths, I guess you get like a decrease of number of modules, but as you remember, the fitness didn't decrease, or it was similar to these approaches. So, and it's again the same for the cuboid base and the flat base. For the, we can see here some videos of the evolved robots, so we can also see some different behaviors. So these are like models with the original length of the robot. So these are like 2 times the original length. And sometimes, I guess, usually these robots, they get like this rolling behavior, which is very nice, very good performance. And then as soon as we just increase the length of the models, these models, they get like thinner, and usually you only get, like when you get like 8 times the original length, you only get like serial change of models. So this is the same video. This is like the video of the flat base. So the same again, this is like the original length of the models, and then we are increasing, this is 2 times the original length, 4 times the original length, and finally 8 times the original length of the models. And we saw this behavior where, like, when the models are small or short, there are like a lot of rolling behaviors, and when the robots are bigger, they just have like this kind of alternate motion where you just go to one side and then they rest there and then go to the other side trying to locomote. Just another graph where you could compare basically the number of models for like the approach with for the different bases, and you can see, I guess, definitely on the number of on the length of the modules, there's always like the flat base always produces results which are like lower in number of modules. So again, and in this case with the first from 1 to 2, I guess the fitness was more or less the same as with the others. So it would be, if you want like have robots with less number of modules, I guess it would be nicer to use a flat base. So this is kind of the discussion that we want to highlight here. I guess as soon as we have like the modules are shorter, the weight of the modules is lower for each module. So I guess the robot can use more modules. As soon as we just expand or extend these modules, I guess the modules get like the robots get thinner, and at the end they have like 8 times its original size. The robots are basically just a serial change of actuators, and this is influenced by greatly by the weight of the modules, because as more weight, I guess the force that the modules can make against the floor is lower, and also because the number of connections start to decrease, because this connection between modules can break if the torque is enough. So as soon as the modules become very heavy and you have like very long chains, they break and they cannot locomote. So basically, that's what is limiting the number of modules in which you have like longer modules. And again, this is some examples with the base robots. I guess we have the same trade-off with the fitness that you want and the number of modules that you will get. And also we have seen how the base influences the morphology, because the base robots get usually less modules, or like the models that use the flat base, they get less modules than the cuboid thing. And interestingly, we haven't observed, I guess, even if they are going, it has like symmetry mutations, we haven't observed any symmetry or just a few of them, or like symmetry robots. And this is probably because the flat terrain favors rolling behaviors over like walking behaviors with different gaits. But interesting, also, I guess, as was seen before, I guess a mixed module length produces robots which fitness close to the best, but with much lower number of modules. So if you can just use a heterogeneous module set, it's always better. But a different nice or hint is that usually, I guess, this around 2 times the original size of the modules is like the is around 100 to 150 millimeters in length, and this is more or less where most of the human designs just end up doing. And so I guess the engineers know what they are doing, because it's one of the regions we produce better designs. So in conclusion, modular robot designers can be used evolutionary algorithms as a tool to find which model designs provide better performance. And without restrictions in the evolutionary algorithm, designers should find a balance between the desired number of models in a robot and their effectiveness. And a heterogeneous system usually gets similar fitness at the best as the best homogeneous systems, but with less models. And future work that we can just try to make later is like try to analyze other properties like motor strength, motor speed, or the connection size, and also evolve in different terrains to see if we can just try to see some symmetry there. So that's it. So thank you very much for your attention. And if you have any questions, I will be happy to answer them.
Thank you so much, Andrés. Very nice presentation, very interesting. And yeah, I think we may have time for one question. Gus is saying nice. You have already one question from Will Landon. Bill, so how well, okay, then two questions. First one, how well does simulation match real robots? Video of simulated robot looks violent. Is it feasible for physical robot to do this without failure?
Yeah, that's a good point. I guess there's always this reality gap that we are trying to overcome. And I guess depends on the behavior. Some behaviors they just transfer nicely. Other behaviors we have this like, yeah, I guess they are exploiting like bad modeled features of the simulators. So yeah, they just hit violently against the floor, and in the simulator that becomes like a big reaction force, which moves the robot forward. In reality, probably they crash and maybe they just break the connection. The good thing about using magnets is that if the connection breaks, I guess the robot doesn't break. I guess it's just disconnected, but you can connect it again without any damage. So yeah, reality gap is definitely a big issue here. The good thing is also that as we can assemble the modules quickly, we can just test them in reality. So and then we could also use that information to just try to just have like some transferability approach or any kind of other feedback mechanism to the evolutionary algorithm.
Okay, thank you so much. We have two more questions, okay? If you are able to respond it quite quickly, yes, please. Not because they are not interesting, but...
yeah. Did you think about using something like map elites of novelty search to fully explore the space of robots with different numbers, weights, size? Yeah. Yeah, I guess that's I guess we are thinking about that too. That's definitely like an approach that we want to explore. I guess we are also more interested also in just trying automate, try to automate these testings in reality, because we have some articles about using an external manipulator to automatically reconfigure the robots. And so I guess we can just have this in automation loop and try to feed this reality or tests into the algorithm.
And then finally, a very quick question from Douglas Diaz, which is, which simulation tools did you use?
Yeah, I didn't say that, but I guess we are using the VREP simulator, which is now called Coppelia Sim since last November.
Okay, so thank you so much again.
Thank you very much. I'm glad that there was no issues with internet.
No, that was perfectly fine. So